Welcome to my presentation. Today I will present LogC, which is classification-based anomaly detection from system logs. Let's dive in. The scale and complexity of large computer systems is steadily increasing to a level where manual operation is becoming infeasible. Today's large distributed systems enable digitalization and transform numerous industries, including healthcare, finance, manufacturing, transportation, and so on. All of this leads to an increasing number of users, infrastructure resources, data, and services where billions of devices and users communicate, compute, store information, and depend on the reliability and availability of these systems. However, due to inevitable weaknesses in software and hardware, these systems are prone to failures. And accurate and timely detection of these failures or anomalies is necessary for reliability, security, and ultimately the mitigation of losses in these increasingly complex systems or for the service providers. Software developers often record critical system information and system status into a log file for purposes of later analysis and troubleshooting. Practically, logs are available on every computer systems, and they are valuable data resource for understanding the system behavior. However, during the recent years and the explosion of data, manual detection of anomalous log is becoming infeasible. So the automation is key. In this presentation, I will present our new method for automatic analysis of logs and in specific the anomaly detection, and we will go through some of the previous work, what is missing in the previous work, and also ways on how to improve this. So a common approach for anomaly detection in logs is one-class classification, where the objective basically is to learn a model that describes the normal system behavior, usually assuming that all the data is unlabeled. If these are on the screen, these are the log messages from a particular system, then we should be able to somehow have a model in the end that will classify each of these log lines as normal or anomalous. Just for like a background, given the log message, which is like a free-form text, the log message is composed of log template and log variable. If you have a look at the first one, which is the total of 77 DDR errors detected and corrected, the 77 is the variable part, and the rest in the bold letters is the template part. Usually, when we analyze logs, we analyze them with the log template. As you see in here, for example, these last two log lines, floating point unavailable interrupt and critical input interrupt, are, however, somehow with the similar meaning, but however, one of them is anomaly and the other one is normal. So from here, you can already see that the problem of detecting anomalies is a hard problem, and we need really understanding of the system or the domain of logs in order to tell if something is failure or not. Previous approaches represented these logs with an indices. So we have the templates here in the bold, and each template is represented by an index T0, T1, T2, T3, and if somewhere in the bottom appears imprecise machine check, it will be again T1. So this is the usual way of representing the logs as a sequence. And then these previous approaches have a model that models these sequences. So they usually consider a window of 8 recent such log keys, like log indices, and they try to predict the next one. If they are able to predict the next one, that means that the model has seen this key during training, and this means that it's most probably a normal. Otherwise, it's an anomaly. However, this approach produces large number of false positives and cannot generalize on unseen logs. Moreover, it's overfitting the data. The bottom line reason is that it uses imperfect or wrong data representations. The indices are too simple representation to represent basically the whole semantic meaning of the log. To further illustrate this, we have a look here at 3 log examples. For example, VM create completed, VM create finished, and VM fatal error. Here in this case, if they are all represented by indices in one hot encoding space, they will be all orthogonal. In a vector space, they will be all orthogonal vectors with no relationship, however. So, in a perfect world, we want VM create finish and VM created complete to be close to each other as data points and to be far apart from the VM fatal error. Basically, to introduce some notion of meaning into the logs in order to generalize better. To demonstrate that the data representation really matters, we assume a linear classifier, and let's assume that the left image on the right side, we have the points in the Cartesian coordinates, and with the linear classifier there is no way to separate them. However, if we change to polar coordinates, as in the right image here, then we are able to perfectly separate them. So the data representation matters, and it changes the whole problem basically. So we need meaningful log representations, and for that we have defined a goal. So the goal is that we want compact normal data, something as in the left image. Compact normal data means that we want all the normal points to somehow be concentrated around a center of some sphere. In a hyperspace would be a hypersphere. In a 2D space would be a simple circle like here. Why? Because we know that all the normal points, by assumption, they are coming from similar distribution, and all the anomalies are somewhere in the tail of the distribution and are distributed all over the space. So we want to develop a method that directly addresses this challenge of obtaining such representation in order for us to be able to separate them normal from the anomalous data. However, the problem is the data. While we have normal data from the system of interest, because we can run, for example, production system or OpenStack instance for like 2 weeks and collect all the normal data, but we cannot find representative anomalies from the system of interest, because this is often very hard. Injections are not allowed because they might hurt the production cloud or whatever system we have. So if we inject in controlled scenarios and we have update in real life, that means that almost all of our knowledge is lost. The anomaly class, however, is really important because it helps to learn more accurate representation of the normal data while regularizing against overfitting. To motivate the approach that we used, numerous deep learning methods, we have a look at numerous deep learning methods that increase their performance by incorporating large amounts of data that is available through the internet. For example, for sentiment analysis, Twitter is not learning from their tweets only and from a labeled data, but they are incorporating large amounts of corpuses like the Wikipedia, the Common Crawl for news, and so on. So we do want something like sentiment analysis, but for logs. We do want to say if the log has negative meaning or is anomaly, or has positive meaning or it's normal. So the question really is, how can we learn such similar knowledge in the logs? We can find such data on the internet as well for logs. We have numerous GitHub projects, but we can crawl them and extract the error log messages that will help us to build such anomaly data. Or we have also open source label data from Usenix, from OpenStack, and so on. Just to point out, that the unsupervised learning in previous research makes sense, but only where access to representative anomalies is not available. In today's settings, we have lots of data and lots of anomalies available, and it's really a waste if we cannot include them somehow to improve our methods. To reach the goal that we defined, which is again stated here on the left side of the image, we need to define, or we defined, a new objective function, and I will just walk through a few formulas here. So if you let phi to be our neural network, or a function, transformation function, that transforms or maps our input log message into a p-dimensional vector representation or p-dimensional space, and this phi is a function or neural network that has trainable parameters theta, which are optimized during the training project, during the training process. We need to define some form of objective function, and this objective function is in the beginning a binary cross entropy. So for binary classification, we always start with binary cross entropy, and this is the standard function. However, in order to reach the desired outcome on the left side, we need to change the binary classification, the standard binary classification, which uses a hyperplane classifier in order to use a hypersphere classifier. And this is obtained by using the Gaussian kernel, which is presented on the right side of the image. Therefore, if we just use this new kernel L, which is the exponential of minus z squared, into the binary cross entropy, we obtain a new spherical binary classification objective. And this classification objective really does what we want to do. For the normal points, it basically says, okay, optimize them to be closer to a center of a sphere, where the center has coordinates 0, 0, 0 in a hyperspace, and throw all the anomalies around. So I don't care about the anomalies, but I care that my normal data stays at the very center. And with this, we have enough knowledge needed, or the background, to just go through the method as the data flows. So at the very top, we have the target system trained data. This is, for example, if we have production cloud, this is the data from the production cloud, which is class 0 or normal. And we have the auxiliary data, and the auxiliary data is this data from GitHub, from online resources for labeled anomalies data, and so on. Of course, we also have the test data, which is the new log data from the target system, which is composed of anomalies, of normal and anomaly samples, and we really want to predict if they are anomalies or not. First, we do tokenization. For example, if we have imprecise machine check as log number 1 and machine check interrupt as log number 2, we tokenize them. Tokenization means that we separate them into words, and moreover, we add this embedding token, this special embedding token, which is used to summarize all, used to summarize all the context from this log message. From the tokenization, the next step is that these tokenized words go into the transformer encoder, which is this function phi, which I explained. I will not go into the very detailed, but the outcome of this neural network is z, which is numerical vector of this embedding token that was added. And you can imagine that this transformer network just transforms your log into a p-dimensional representation, which is z in this case. And with this transform log into a space, we have a numerical representation of the log. This numerical representation can be used directly into our training function, and via the backpropagation algorithm, the parameters are updated, and in this way we learn a model. For detecting anomalies, We know that the objective function enforces normal samples to be close to the center of the sphere. And I said that the center of a sphere is always a 0. So in optimization, doesn't really matter where you fix the center. So we take the center as a 0. And we define the anomaly score as the distance of the log vectors obtained, the Euclidean distance of the log vectors to the center C of this sphere or hypersphere in hyperspace. If the anomaly score is larger than some threshold epsilon, then it's an anomaly, else it's normal. That's our decision function. So the experiments. The experimental setup is consisted of 3 benchmark data sets, and these are to best of our knowledge, the only 3 data sets which are really manually labeled, large data set which are really manually labeled and collected through many days. As you can see here, we have of around 200 to 600, almost 600 days of collection data. We always split the data in this way. So we have a target data set, for example, the blue gene. We split it into a train and test split. The train split contains only normal class, and the test split contains normal and anomaly class, and this is used for only evaluation. Where the auxiliary data is the anomaly samples from the other data set. We can use this because these 3 data sets are from different vendors and they have all different kinds of logs, normal and anomalous logs, so they don't have any overlap between them. Moreover, to ensure that we always have new unseen logs into the test split, we do perform several splits like 10, 20, 40, 60, and 80%. And here in the table you can see really the numbers. So, for example, in the test split, when the split is 10%, we have around 2,500 new unseen logs into the test, and so on. You can see here the numbers. The overall results are pretty promising and outperform the previous method, which is deep log, which is fully unsupervised, and also outperform the pretty baseline, which is the PCA. We can see from these graphs that in F1 score we can see that it outperforms, but really we can see why it outperforms in the precision table here. In the precision table we can see that the outperformance is by a large margin, and this is only due to reducing the false positive predictions. These unseen logs, which deep log, for example, will predict always them as an anomaly because it never seen this index, we are making really large improvements in this area here. We also tested the effects of the auxiliary data, where we started from only 1 sample of auxiliary data to up to 250,000. And we can see that already at 10,000 we have, already at 10,000 we have already the best performing model. So no more samples than 10,000 logs are needed. The next question we try to answer is that if data is available, like if expert data is available, for example, if an operator have a look at the logs and says, okay, this log is misclassified, can we include this label data into our method? And the answer is yes, because binary classification inherently enables inclusion of labels, which is not really the case with fully unsupervised learning. And with including almost 2% of the data, we already reach state-of-the-art performance, as you can see here in the F1 recall and here in the F1 recall and precision scores. In order to conclude the evaluation, we also performed evaluation on how good are the learned log representations. And we did dimensionality reductions of these p-dimensional log representations via t-SNE, and we exactly have here what we hoped for. So we have the normal data more or less concentrated into a circle, and we have all the anomalies dispersed into the space. Also, when you have a look at the distance, you observe the same. Finally, these log representations are not only useful for log-C, but also can be used in other previous methods. For example, we tried to replace the standard log representations used in PCA with our log representations, and we saw an improvement of around 28% in relative F1 score. To conclude the presentation, we presented log anomaly detection method, and we stated why log anomaly detection is important for computer systems. We said and we proved that existing approaches lack generalization on new and unseen log samples. We proposed new problem formulation as binary classification with the use of auxiliary data. We outperformed the previous state-of-the-art by a large margin of around 0.25 in average F1 score, and we showed that the method learns meaningful log representations, where we proved in PCA, for example, and improved the performance of PCA by 28.2% in the F1 score. As final remarks, it is reasonable to assume that access to anomaly data, informative for detection, is available today, and not like in the traditional setting. And in support of our results, we believe that the future research on deep log anomaly detection should focus on incorporating domain bias that describes the diversity of normal and anomaly data. Thank you for your attention.